Hello students and welcome to another video lecture on logic design. In this video, we are going to take a look at another category of numeric codes called error detecting and correcting codes, namely Hamming code. Hamming code is a block code that is capable of detecting 2 bits of error and correcting a single bit of error. It was developed by an American mathematician called Richard Hamming. It makes use of parity bits that are located at certain positions in the code group. There are 2 parts to working with Hamming code. The first part involves encoding a message using Hamming code, and the second part involves decoding a message using Hamming code. In this video, we are going to look at an example which demonstrates the first part. Let us start by encoding data using Hamming code. Given the data bits 10, 110, we want to encode this using Hamming code to create a single bit error correcting code using odd parity. Step 1 in Hamming code procedure is to decide on the number of parity bits. If the number of data bits is given by m and it is equal to 5 in this case, then we have to find the number of parity bits p. The relationship between m and p can be given by an equation 2 raised to p should be greater than equal to m plus p plus 1. We find the value of p using trial and error method. If we take p as 4, then this satisfies the equation since 2 raised to 4 is greater than or equal to 5 plus 4 plus 1. Therefore, the number of parity bits we will use in this example is 4. Going to step 2 of the Hamming code procedure, which says placement of parity bits. Now that we have found that we need 4 parity bits for creating the Hamming code word, we need to see how to place them. Remember that the total size of the code word is m plus p, where m is 5 and p is 4. This equals to 9. So we can assume the code word to look like this. Notice that each bit position starting from the right is labeled with a number, that is, the bits go from numbers 1 to 9. Now Richard Hamming designed this code by placing the parity bits at positions labeled with powers of 2. So the first parity bit will be placed at position 1. The next parity bit will be placed at position 2. The next parity bit will be placed at position 4. And the last parity bit will be placed at position 8. Since 1, 2, 4 and 8 are all powers of 2. I have named the parity bits P1, P2, P4 and P8. The rest of the empty bit positions are for the data. So starting from the LSB, let us proceed and add the data. This completes step 2. Step 3 of Hamming code procedure states assignment of parity bits. We are basically left with this after step 2. For reference, I will name the data bits starting from the left and going right as D9, D7, D6, D5 and D3. Now each parity bit will check those data bits whose binary code has 1 in the same bit position. For this, we need to assign binary codes to each bit position. Doing so makes your code look like this. So, parity bit P1 has 1 in the first bit position. Hence, it will check the data bits D3, D5, D7 and D9. Similarly, parity bit P2 has 1 in the second bit position. Hence, it will check the data bits D3, D6 and D7. Parity bit P4 has 1 in the third bit position. Hence, it will check the data bits D5, D6 and D7. Parity bit P8 has 1 in the fourth bit position. Hence, it will check data bits D9. So, I will put the values for D3, D5, D7 and D9. For odd parity, P1 needs to be made equal to 1. Next, I will put in the values for D3, D6 and D7. For odd parity, P2 needs to be made equal to 0. Next, I will put in the values for D5, D6 and D7. For odd parity, P4 needs to be made equal to 1. Next, I will put in the values for D9. For odd parity, P8 needs to be made equal to 0. Replace all these values and you get the final code as 100111001. This is your Hamming code word. That's all for now. Stay tuned to the classroom for another video on decoding using Hamming code.